All right, let's talk a little bit now about reaction mechanisms, all right, and how the rate is kind of related to a reaction mechanism. In a reaction mechanism, we have different steps that can occur, right? So we already talked about an energy diagram, for example, where this is energy versus time, and we have our reactants. There is an activation energy, and then perhaps there's an intermediate with another activation energy, and then some products, right? So here's our reactants, here's our products, right? And this we call an intermediate, the energy required to overcome these activation and overcome to allow new bonds to form. That's called the activation energy, right? We've talked about this. All right, and we could think about our reactants maybe being A and B here, and maybe our product here is D, but maybe at this point here something else is formed, like maybe it's C and E are formed. So we could think about our reaction. It would be A plus B forming our product D. However, if we were to look closer, we would see that what's happening here is A and B are coming together and forming C and E. And then C and E are coming together to form D. The overall reaction is this, but the two steps that we kind of add together to form, or to have this reaction occur are these. These are what we call the mechanistic steps, the mechanism, the little intermediate steps along the way. We never really see any C or E in this reaction because all we're looking for is the reactants and the products. And so these intermediates are short-lived. We don't really see them, all right? But these steps, which we call elementary steps, sum up to form the overall reaction. And these steps can be give us information about the rate determining step, or what is governing the rate of a given reaction. So here's some examples of elementary reactions where A just goes right to products, right? There's no steps in between. Two A's can come together to form products, A and B coming together to form products, multiple things coming together to form products, right? All of these can have rate laws accordingly, okay? We have catalysts which can lower activation energy. Now, so if I had a catalyst for this reaction and I wanted to include it, let's say Z is my catalyst, right? Well, a catalyst is something that it goes in as something, but it comes out as exactly the same. It comes out exactly the same. So a catalyst isn't changed, and in fact, you won't see it in the reaction like that because it doesn't undergo any chemistry. It helps what we call the substrates now, when we're talking about a catalyst, react and perform their chemistry, but it doesn't change itself, all right? So a catalyst you won't see in the chemical reaction. Sometimes you'll see information about the catalyst drawn over the arrow like that. Intermediates also you see here in this reaction that we had where A and B are forming D. The intermediates C and E aren't shown in the chemical reaction because they form and then are consumed later on. But we have both catalysts and intermediates in our reaction. So here's an example of a process, and we want to see which is the rate determining step, first of all, and if there are any intermediates in this mechanism, or in this reaction. Now, this is the mechanism. These are the mechanistic steps for the reaction. And you know, if we wanted to see the overall reaction, we'd have to add these two together. So if I add number 1 to number 2 here, right, I'm going to put all the reactants on the left of an arrow and all the products on the right of an arrow. What would I get? What would my resulting reaction be if I added these together?
Oh, you mean like 2 H2Os? 2s?
That's right. 2 H2O2s, 2 hydrogen peroxide.
Plus an I minus plus an IO minus. And then on the other side, you have 2 H2Os plus O2 plus IO minus plus I minus.
Okay, now we would end up not including these in the reaction, right? Because if it's the same on the reactants and the product side, no chemistry has occurred there. So all we have is 2 hydrogen peroxide going to 2 waters and, oops, this isn't 2, this is O2. Okay, so there's our chemical reaction that's occurred. But we see then that I and I minus and IO minus aren't in the reaction. I is added, but it ends up being there in the end. So what do you call that? Something that's added that apparently helps the reaction proceed, but then is there in the end.
Oh, that's a catalyst.
That's right. IO is formed in one of the steps, but is consumed later on. So what do you call that?
Oh, that's an intermediate.
Very good. So we have an intermediate, IO minus. They didn't ask about the catalyst, but we see that I minus is the catalyst. And we didn't address this directly, but the slow step has the greater activation energy and therefore is going to be the rate determining step. In this energy diagram, if we were to draw the energy diagram for this reaction, we have the energy for our reactants. All right. We don't know if the products are higher or lower. I mean, I actually do know because of experience, but it doesn't matter in this case. But we know that there is a slow step, has an activation energy, and we don't know the energy of the relative energy of the intermediates. And then there is a fast step, which has going to have a lower activation energy compared to the slow step. And really, it doesn't matter how much lower this second activation energy is, because if you've reached this much energy, then the second step is going to be inconsequential in terms of rate limiting the process. Okay, very good. So there is this relationship between the rate law and the mechanism if you know the slow step. So our observed rate law will usually match the slow step in the reaction. So if we have mechanistic steps here and we want to write the rate law for the reaction, usually what we would do is we would say rate equals K times our reactants here, hydrogen peroxide. Now, I minus is a catalyst, so we're not going to include it, all right? Although it will, the rate of the reaction will be dependent on its concentration, okay? But I'm just going to include the rate based on the concentration of hydrogen peroxide at this time, all right? How would we identify what this rate law is, what the X is there?
You would, oh, it was a long time ago. I can't remember. What do you do?
Remember, we performed the reaction at 2 different concentrations of hydrogen peroxide, which we have reacted here, and find out how that affects the rate of the reaction.
Oh, yeah, okay, I remember. And then you see if doubling the hydrogen peroxide, for example, doubles the rate. And if it does, then X is 1. If it doesn't, then if it stays the same, the rate, then X is 0. And if it quadruples the rate when you double the hydrogen peroxide concentration, then X is 2.
Very good. That was a good recap, good review. Now, what we're introducing now, though, is that if I have the mechanistic steps, then the rate law, this X here, will actually be the coefficient on the hydrogen peroxide in this slow step. So here, because the hydrogen peroxide is 1, I can say that the rate law is K times the concentration of hydrogen peroxide to the 1.
How did you know that?
Well, again, if you have mechanistic steps and you can pick out the slow step, then the dependence of that slow step is going to be related to the coefficient on that chemical reaction, on the chemical reaction for just this, the mechanistic reaction for just the slowest step. So because this is a 1 here, that's how I can know the rate law. All right. Another way, okay, so here's another example we can practice that concept.
Okay, so there's reaction there. We have mechanistic steps, and we're supposed to get the rate law?
That's right, we're supposed to be able to get the rate law here.
Well, rate will equal the concentration of... Can I include C in there?
We don't include C in there because C is a what?
What do you call it when it shows up and then disappears?
That's an intermediate.
Oh yeah, C is an intermediate.
Very good. So I put in A and B, and then I form C. C is consumed with a second B to form D and E. E is consumed with a third B to form F. If I look at the overall reaction here, there's A, 3 B's, a C, and an E on the left, but the C and the E are consumed, and the D and the F are what is left. So we have A plus 3 B's forming D and F. You see that? The C's cancel out, the E's cancel out. I have D and F left over, and I have to put in an A and 3 B's to get that overall reaction to occur. So we might expect, I mean, somebody would be tricked if they didn't realize that to identify the rate law, you have to do it experimentally, right? Remember, we just mentioned that. You have to double the concentrations of A and double the concentration of B and see how that changes the actual rate. But if we have the mechanism and a mechanistic step, the slow mechanistic step here, and we know that A and B are possible contributors to the rate law, we can say that the rate is going to be K times B to the 1, because B has a coefficient of 1 in the slow step. Oh, and they included C. We shouldn't include C in this, actually. But if you wanted to know how it's dependent on the intermediate for some reason. But I should actually fix that. Okay, good place to stop.